drill bit leads to the disappearance of an entire lake and everything in it. The tallest man-made structures in the world turn to crumpled steel. A poorly designed dam wipes out an entire community in minutes. A freeway collapse in earthquake country. And the worst oil spill in U.S. history. Now, engineering disasters have been obsessed with the idea of building the tallest structure in the world. From the ancient pyramid of Khufu, which stood as man's highest creation for 43 centuries, before being eclipsed by the Eiffel Tower, to the 20th century's skyscrapers, which jostle for top rank as they push ever higher. The desire to be on top, looking down, is an enduring one. But all these magnificent structures fall far short of a stark utilitarian tower that rises up from the plains of North Dakota to a vertiginous height of 2,063 feet. Meet the KVLY Broadcasting Tower. Its antenna stands 356 feet higher than the tip of the antenna on the Sears Tower, higher than any other structure on Earth.
They are very impressive structures, and yet when you drive by them, they don't look like much. In fact, they're even hard to see under certain conditions. But there is an awful lot of very sophisticated engineering that goes into designing them.
FM and television waves can't go around obstructions, and thus require a very high launching pad to reach the desired coverage area. In regions of the Midwest and South lacking tall mountains, the solution is to build a tower of extreme height, like the KVLY tower. The most characteristic design feature of broadcast towers is this steel lattice framework, which is bolted together in 20 to 40-foot sections, all the way to the top. A less noticeable but crucial part of the tallest towers are thin steel cables called guy lines. These high-strength pre-tensioned cables stretch down from the tower at several vertical points and are anchored into cement foundations on the ground.
Basically, a guy cable is a tension element. The only force that it sees is tension. It can't take any other force. The guy cables are not carrying any gravity loads or any weight. They're only resisting the tendency for the wind to push the tower over.
Since they anchor the tower to the ground, guy lines prevent antenna towers from being considered the highest freestanding structures in the world. They can also play a key role in a tower's collapse. This is the view from an antenna tower in Missouri City, Texas, on the final day of its construction, December 7th, 1982. Known simply as the Senior Road Tower, it was to be 1,971 feet high. Less than 100 feet kept it from being the tallest structure in the world. An hour after these pictures were taken, it would be reduced to a crumpled mass of steel.
The basic tower structure was complete, and the first portion of the antenna had been installed. The antenna was a very large broadband antenna for multiple FM stations. It was built in two sections, each of which was about 60 feet long. And they were lifting the final section, and it was moving up the tower about halfway.
The FM antenna weighed 6 tons. The 5-man rigging crew had constructed a hoisting device called a gin pole, specifically for this job.
When you are building a tower, you typically cannot reach it with a crane. So if this is a tower, we hoist a gin pole up the side of it and we put it up higher than the tower. Now from the top of that, we can put something on the top of the tower.
In a dangerous maneuver, 3 of the 5 men were riding inside the antenna as it was being lifted, while the other 2 were on the tower itself.
You're mostly focused on the work that you have to do and the task at hand and staying alive and not falling off.
At about the 1,500-foot level, the U-bolts on the clamp bearing the weight of the antenna failed. The antenna and the men attached to it fell toward the ground.
Oh my God!
At 1,000 feet, the antenna sliced one of the 27 guy lines that held up the tower. The tower sprang in one direction, whipped back the opposite way, and collapsed with a thunderous roar.
Say that one of those cables had a tension in it of, I'll say 20,000 pounds. And then you suddenly break that, So you release that kind of energy. The other cables that are still intact are pulling by that amount of force the other direction. And so they pull the tower sideways, and that causes it to buckle.
The stunned contractors ran to the scene of destruction. All 5 men were dead.
Is anybody in this stuff?
The transformation from sky-high tower to tangle of steel took 17 seconds. The total collapse of the senior road tower was caused by the guy line snapping. But the disaster was set in motion by the failure of the half-inch diameter U-bolts on the gin pole. During the subsequent investigation, analysis would show that the shear strength of the bolts was half what it should have been. Some observers believe these small puffs of smoke are actually debris flying off the bolts as they snapped. According to the investigation, the riggers had not consulted with a licensed engineer when selecting the U-bolts. Tall antenna towers and the brave men who work on them are still at risk during construction and maintenance. Between 1992 and 2002, 163 people died in tower accidents. For engineers, the challenge is to reduce the risk of catastrophic failure during moments when the forces acting on the tower are being shifted.
For instance, if they're replacing a brace, what happens is they go up there and they take that brace off. Once they take the brace off the tower, now the tower is vulnerable.
Natural forces also pose a threat. Ice and wind, especially acting together, can bring a tower down.
So you have the weight of the ice itself, and then you have the increased area that's exposed to the wind due to the thickness of the ice coatings. And this can increase the wind forces considerably.
But it's the collapses during routine construction and maintenance that continue to echo lessons not learned from the tragic senior road tower disaster. These collapses, which most often involve the loss of human life, are the most preventable.
It is an industry that does have some hazards to it during construction, and you certainly have to be extremely careful. And there's been a big increase in the attention being paid to the safety issues during construction.
Which is good, because humanity's hunger for instant information, communication, and entertainment is only increasing.
Communications off of towers and mountaintops and broadcast sites is the backbone of our entire society. With all of our communications, police, fire, ambulance, television, radio, two-way radio communications, all sorts of communications are being handled by these tower sites that you don't even realize.
Another vital resource moves all around us 24 hours a day. Oil. We don't think about it until disaster strikes. If a baseball were dropped from the KVLY tower in North Dakota at the beginning of this sentence, it wouldn't hit the ground until 6 seconds into the next commercial. Engineering disasters will return on Modern Marvels. We now return to engineering disasters on Modern Marvels. It grabbed front-page headlines and filled television news time for months. The images of dead and dying wildlife and hundreds of miles of pristine coastline choking with crude oil saddened and angered the public. Another image was burned into the public's consciousness as the media focused on an allegedly drunken captain who had steered his boat into a reef. But there's a lot more to the story. The Exxon Valdez oil spill, the worst in U.S. history, was also an engineering disaster.
The human element in the Exxon Valdez is multidimensional, and people focused again on the simplistic issue of the Captain Hazelwood. And we like to be able to point the failure at one person or one thing, and you know, if Joe Hazelwood had not had that last drink, everything would have been okay, and not seeing the complexity of the incident.
We're approaching the Exxon Valdez. She's hard aground. She got the starboard slop tag, starboard wing tank, and possibly 5 center are impacted.
The grounding of the tanker Exxon Valdez on Bly Reef occurred at 4 minutes after midnight on March 24, 1989. A clear night with calm seas.
You can see a black oil line right here. The vessel has lost 105,000 barrels of oil so far.
The massive tanker, nearly as long as the Chrysler Building is tall, was carrying 53 million gallons of North Slope Alaskan crude. Oil from the North Slope makes an 800-mile journey through the Trans-Alaska Pipeline to the port of Valdez, where it's pumped into tankers.
The North Slope oil and the pipeline to Valdez and the sea leg from Valdez to the west coast of the U.S. was a highly political decision when it was created. You may remember that the bill to create the pipeline was passed on a tie vote.
The immediate cause of the accident was fairly simple. Captain Joseph Hazelwood had ordered the ship to leave the outbound shipping lane and head inward to avoid icebergs, a fairly common move in Prince William Sound. Hazelwood then left the third mate, who had steered supertankers through the Sound 25 times previously, in command of the ship. To re-enter the shipping lanes before running into Bligh Reef, the Exxon Valdez would have to make a hard right turn.
This is not a sports car you're driving. This is a 200,000 deadweight ton tanker. And when you give a rudder command or an engine command, it doesn't instantly change.
The third mate had a relatively inexperienced seaman assisting him with the turn. The 987-foot tanker failed to make the turn in time. Traveling at 12 knots, the ship slammed into the rocky bottom of Bligh Reef and ran full aground. 8 of its 11 cargo tanks were torn open. Oil gushed freely into the sea. 11 million gallons would enter the water. In his call to the Coast Guard, Hazelwood made one of the great understatements of all time.
We should be on your radar there. We fetched up hard to ground north of Goose Island, Bligh Reef, and evidently leaking some oil.
Human error had played its part, but the ensuing disaster would reveal a fatally linked chain of engineering as well as human failure. The most immediate failure was with the ship itself.
When the Exxon Valdez happened in 1989, when that ran aground, the whole issue of these monster ships that carry these massive amounts of oil, the issue of the ship having only a single hull came to light.
The Exxon Valdez was only 2 years old, yet only 3/4 of an inch of steel was all that stood between millions of gallons of oil and one of the most environmentally sensitive areas of the United States. The long-awaited catastrophe of the single-hulled supertanker had arrived when the controversial Trans-Alaska Pipeline began operations in 1977. It came with promises that all tankers would be outfitted with double hulls.
Think of a U for a cross-section of a supertanker. Then think of a smaller U inside with a 10-foot difference in between. So it's basically a hull inside a hull. That's why they call it a double hull.
And so if there is an impact, the energy of that impact hopefully is taken up by penetrating the first hull, but not the second one.
The double hull was a promise not kept or enforced. In 1989, nearly all of the tankers leaving the port of Valdez had a single hull. But the ship itself was only part of a complex oil transport system that had broken down. A systems failure.
There were assurances given by the oil companies that it would be operated in a fail-safe mode. And sometime between 1977 and 1989, the operations of the system had degraded to a point where a very severe accident could occur. When you get to a system where one mistake means that you lost the whole thing, then you really haven't designed the system very well.
A key part of the system's failure was inadequate radar. Shortly before the disaster, the Valdez Coast Guard station's radar crews had been cut in half, and the radar itself had been replaced with a unit that was no longer capable of detecting Bligh Reef.
So when the Exxon Valdez was heading for Bligh Reef, it was not under any external radar coverage.
Reductions in the tanker's crew size, nearly 50%, further increased the chance of disaster. The final weak link in the chain was the spill response.
If the strategy was, if you have a major oil spill, to contain it near the ship to minimize damage and then remove it from the containment, actually the response was a total failure because the oil totally escaped from the vicinity of the ship.
Nearly every technology used to clean up the oil spill arrived too late and was ineffective. Many of the containment booms, large floating curtains used to corral the oil, were of the wrong type for ocean use. Some actually sank. Fishermen with buckets reportedly had better success in scooping up oil than Exxon did with skimmers, mechanical vacuums that suck up oil. And when foul weather arrived on the third day, whipping up the oil into a thick mousse-like froth, it was too late for chemical dispersants to be effective in breaking down the oil.
The initial cleanup was a total failure because there was inadequate resources. The people of Alaska justifiably felt betrayed. They were told that if anything happens, we have the equipment, we have the skills to clean it up, and that was not there. It's a pristine region. If you've ever been there, Prince William Sound is incredibly beautiful. So the environmental damage was proportionally very high for the amount of oil spilled. Then it just became just a massive shoreline cleanup and restoration exercise, which took months and it cost a lot of money, and it's still doubtful what good that actually did.
The good that did come out of this disaster, and the Oil Pollution Act of 1990, came in the form of better tug escorts, which can tow or nudge the giant tankers away from danger. GPS systems in concert with improved radar, dramatically improved cleanup technologies, and a mandate that all U.S. tankers have double hulls by 2015.
The accidents have always led to the change of design. Engineers, we learn from previous screw-ups, and we look very carefully at previous engineering disasters.
While oil spills continue to plague the seas, at least one region, ironically, is ready.
The irony is probably the only port in the world where you are absolutely prepared for a major oil spill is now Valdez.
If preventing man-made disasters is difficult, engineering for natural disasters, especially earthquakes, is a mammoth challenge. According to a U.S. Coast Guard report, of the 15 double-hull accidents between 1990 and 1999, none resulted in any oil spilled. Engineering disasters will return on Modern Marvels. We now return to engineering disasters on Modern Marvels. California. Its very name evokes the idea of a promised land. But the Golden State has always paid a price for its prime location. Raging wildfires, drought, and giant waves that batter its coast. Of all the natural disasters that plague California, the deadliest and least understood are earthquakes. The threat of the big one will always pose a daunting challenge for the state's engineers.
It's not like these hurricanes where you can line up and prepare. I guess the bright side is we're kind of competing against time. The longer this big earthquake takes to occur, the better prepared we're getting.
The most painful lessons have taken place at the vulnerable connecting points of California's gigantic circulatory system. Freeway bridges. One particularly tragic incident sent shockwaves through the engineering community. The collapse of the Cypress Viaduct structure in Oakland during the 7.1 Loma Prieta earthquake on October 17, 1989. The quake lasted 12 seconds, and although the epicenter was 50 miles to the south, the worst structural failure and greatest loss of life would occur here when a 1¼ mile upper deck section of the 880 freeway pancaked onto the lower deck. 42 people died, crushed in their cars. The detached, unstable structure made rescue efforts difficult and dangerous.
It was a progressive collapse. A failure occurs in some localized area, and because of that failure, the loads then are exceptionally high as they're transmitted to other parts of the structure.
The immediate cause of the disaster was the failure of certain support columns. The intense horizontal movement of the earthquake caused the columns to shear outward, leaving the upper roadway no place to go but straight down.
The top part of the roadway had relatively small columns, and there were deficiencies right where the columns from the upper level sat on, or essentially met the roadway at the top of the first level.
The column failure demonstrated an especially cruel quirk of earthquake behavior.
Most structures are designed to resist vertical loads. When you have the earthquake, you're applying lateral loads. And so for a good earthquake design, you must not only design the structure to take its weight, but you must design the structure to take these lateral loads that would tend to push it over.
When the Cypress Viaduct was completed in 1957, it was the state's first double-decked freeway bridge. Engineers thought they had built in sufficient redundancy by designing it with 2 sets of columns instead of 1. But they didn't count on the dramatic increase of destructive force caused by the ground itself, a phenomenon known as soft soil amplification.
The Cypress structure is located fairly close to the San Francisco Bay, and the soils underneath it tend to be soft soils. They call it bay mud. And at the Cypress structure, there's the ground accelerations, which might have been 0.05 G, are amplified, so by the time you hit the foundation of the Cypress structure, there may be 0.25 G, or a 5-fold amplification.
G measures the rate of ground acceleration as a percentage of the Earth's gravity. The Cypress was built to withstand only 0.06 G. This flaw stems from the fact that the Cypress, like many of California's freeway bridges, was built during a 30-year lull of major earthquake activity. There simply hadn't been enough big quakes to learn from. Fast forward to 1994. The California Department of Transportation, or Caltrans, began building a new, meticulously engineered Cypress Viaduct in the shadow of its former self. But just as work was beginning in Oakland, the 6.6 Northridge earthquake struck, 400 miles to the south in Los Angeles, where 8 freeway bridges collapsed, some shearing in half, others simply falling down. Only the earthquake's timing, it struck at 4:30 a.m., kept freeway fatalities low. The Northridge quake brought into sharp relief the urgency of fixing California's freeways. Back in Oakland, Caltrans engineers and contractors, once again armed with hard-won knowledge, continued their work. The new Cypress structure would be an engineering achievement. It would be marked by advanced use of a fairly new concept in freeway design: flexibility, or ductility.
One of the essential features of ductility is that if you exceed the strength of the structure, it doesn't fail. It can deform, but it doesn't collapse. And this is the concept which is now being put into the design of modern freeway structures.
The bend but don't break concept was realized dramatically in heavily reinforced cast and steel shell, concrete piles, sunk as deep as 90 feet into the bay mud, and in vastly improved connections where the columns join the roadway. The new Cypress Viaduct has been designed to withstand 1.8 G of peak horizontal force, or 30 times greater than its original strength. It's a model for the future of California's 12,000 miles of freeway, and the type of extreme engineering needed for those who live in the seismic hot zone.
There are many things that have been done to improve the safety of bridges for earthquakes. And by and large, through a learning process, the bridges are a lot safer in California now than probably anywhere else in the world. That doesn't mean we still don't have more to do.
But in the heart of America's coal mining country, a blatant failure of engineering would be necessary to spark reform. During the 1995 Kobe, Japan quake, a 1/3 mile section of expressway collapsed, killing 16 people. Like the Cypress structure, its failure was caused partly by the soft soil on which it was built. Engineering disasters will return. We now return to engineering disasters on Modern Marvels. This is Buffalo Creek, West Virginia, a steep, rugged valley in the heart of Appalachia. The surrounding region of Logan County became known as the birthplace of the Hatfield-McCoy feud, and later as one of the most prolific producers of coal in the United States. But since February 26, 1972, it's better known as a place torn apart by a dreadful engineering disaster, one that killed 125 people and forever altered a community. the roots of the disaster. Other disasters defy prediction and belief. Next, a spectacular chain of catastrophe is unleashed in Louisiana. There are over 650 coal waste dams in the United States today. At least 232 are in West Virginia, more than in any other state. Engineering disasters will return on Modern Marvels. We now return to engineering disasters on Modern Marvels. The southern coast of Louisiana, where the water flows everywhere. Shallow lakes full of catfish, broad bayous, canals dotted with shrimp boats, all leading to the Gulf of Mexico. On November 20th, 1980, water would play the key role in one of the strangest and most spectacular engineering disasters ever. This was once the shaft of the Jefferson Island salt mine, where men had been pulling salt out of the earth since 1919. Louisiana's salt lies in gigantic underground domes, some larger than Mount Everest, which are pushed upward by the force of the heavier rock that surrounds them. Part of the Jefferson Island mine is located directly under Lake Peigneur. The mine, which was operated by the Diamond Crystal Salt Company, shared space on Jefferson Island with a lush botanical preserve known as Live Oak Gardens. There's another abundant resource deep under Lake Peigneur, one frequently found in pockets near salt domes. It's as black as the salt is white.
That salt moves upward and it pierces through surrounding strata, sands, clays, and limestones. And this piercing produces faults and folds within these surrounding sediments, producing an ideal mechanism to trap oil.
So it was hardly surprising that Texaco was conducting exploratory drilling close to the Jefferson Island salt mine in November of 1980. On November 20th, the two delicate underground and underwater operations, drilling oil and mining salt, collided in spectacular fashion.
Well, it was a typical day in November the 20th, 1980. A nice, cool, crisp day, clear skies. People were fishing out on the lake, as they usually do. The mine was in full operation.
But in the pre-dawn hours, the oil drilling crew on Lake Peigneur had run into a problem.
At 500 or 600 feet, they hit salt. And they were not supposed to hit salt for another couple of 100 feet.
The drill bit became stuck. The crew heard strange popping sounds. The oil rig tilted badly to one side.
And at that point in time, the drillers recognized that they had a fairly serious problem on their hands.
What they didn't realize is the 14-inch drill bit had punctured the roof of the salt mine at the 1,300-foot level, creating a funnel for Lake Peigneur to drain into. It was apparently the result of a simple miscalculation.
It seems that there was an engineering error in the location of the Texaco well. They used a form of triangulation for determining the location, and one of the points they used for triangulating was in error. And consequently, it rotated the location of the borehole about 400 feet closer to the main mine than it should have been.
90 minutes after the drill became stuck, the drilling crew, who had wisely abandoned the tilting rig, watched in amazement from the shore as their 150-foot derrick disappeared into a lake that was less than 10 feet deep. Meanwhile, 1,300 feet below the surface of Lake Peigneur, Diamond Crystal miners, who had not been alerted to a problem, looked up to see something you should never see in a salt mine. Water.
Water flowing through salt tends to dissolve the salt. As you increase the volume of water, you increase the volume of salt that can be dissolved.
Soon it was clear. Lake Peigneur was draining through the hole bored by the drill bit and into the salt mine. As the 2.5 billion gallons of Lake Peigneur surged into the mine with 10 times the pressure of a fire hydrant, a mighty whirlpool was forming on the surface. Remarkably, thanks to well-rehearsed evacuation drills and the heroics of several miners, All 55 people in the mine managed to get out. But back on the surface, the chaos was just beginning.
The whirlpool is basically a vortex of water and mud that is flowing down into a fairly confined space. And that whirlpool is basically flowing downwards under the force of gravity, pulling sediment and other materials down with it.
The whirlpool's sucking force pulled heavy-duty barges toward it as their crews leapt for safety. Men watched with jaws agape as 11 barges and a tugboat disappeared into the vortex. Those are 4 fully loaded flatbed trucks spinning helplessly in the whirlpool. Enter Leonce Viator Jr., who had simply wanted to catch some fish that day.
I was crazy enough to be on the lake November the 20th, 1980. So I asked my nephew to come with me on the boat and was gonna go catch some catfish. We went. We're gonna go and try our luck.
But as luck would have it that day, Viator soon found himself and his 14-foot boat being yanked toward the whirlpool and certain death.
When we got further down on the lake, I spotted something, an eye in the ground. To me, it measured 100 feet in diameter. And there was a lot of barges all glued to it. I didn't know what was happening.
When a barge that was blocking the way was sucked into the hole, it gave Viator a narrow path to skirt the maelstrom. He gunned the motor and reached the shore with seconds to spare. Viator then tied his boat to a tree.
When I looked like this, I seen my boat that I had tied to the tree, and there it was going into the whirlpool. So that's the last thing I've seen, my boat tied up to the tree going into the hole.
By that point, the whirlpool was sucking down Jefferson Island itself. Before evening, 65 acres of land, including much of Live Oak Gardens, would end up at the bottom of the mine. 150-year-old trees were snapped in half.
There were pecan trees that were 150 feet tall down here in this woods, and to stand there and watch them drop completely out of sight was, yeah.
Along the shoreline, along the Live Oak Gardens and the Jefferson Island Mansion, you're basically seeing what are called landslides, where the ground is actually shearing and breaking apart, and gravity's pulling these blocks down into the hole.
Look at this over here, look! Look at that going in there. Look at all the trees going. Look at this!
That house that we were standing on, all you see now is a chimney. The house sank about 30 feet.
Could things get worse? Yes. Delcom Canal, which normally flowed away from Lake Peigneur and into the Gulf of Mexico, actually reversed direction under the intense sucking power of the whirlpool. As the water rushed into the now nearly empty lakebed, it formed a 150-foot waterfall, the highest ever in Louisiana.
But that's the only time the Gulf of Mexico flowed north, basically. So that's a lot of water, to fill up that hole.
As the water rushed into the mine, its rapid displacement of the underground caverns shot a deafening blast of compressed air, and later, a 400-foot geyser up from the mine shaft.
To see something like this, it was terrible, really. I thought it was the end of the world.
It took 2 days for the canal's water to fill up the mine and Lake Peigneur. When the water pressure equalized, 9 of the 11 sunk barges popped up like corks in a bathtub. The drilling operation and the underground salt mine were complete losses. The cause of the disaster was never officially determined, since all the evidence was at the bottom of a 1,500-foot water-filled salt mine. But there's no definitive evidence that the mine itself was structurally unsound. The culprit was most likely a 14-inch wide drill bit. This engineering disaster did have at least one positive effect. It made Lake Peigneur a little more interesting.
It's a shallow lake, and now we have part of it that's a deep lake. So it's changed the type of fish that live in the lake, and we catch redfish and saltwater species that were not very prevalent here before.
But not everyone is planning a fishing trip to Lake Peigneur.
What I went through and got out of there alive, I don't care for it, really. I prefer buying my fish.
It can hardly be said that the Jefferson Island disaster had a happy ending. The loss to livelihoods and cherished property was devastating. Yet the fact that no human beings perished was fortunate indeed. For if there's one lesson to take from this strange engineering disaster, it's that a small mistake can have huge consequences.
Think the first Superdome was opened in 1965? You're about 2,000 years off. Think the first gated communities were built in the 1980s? Think again. The Romans, they not only conquered the ancient world, they conquered the future. Rome, engineering an empire. Tonight